In the summer of 1965, a once-in-a-lifetime planet alignment was discovered. This alignment occurs once every 176 years. Calculations revealed that it was possible for a spacecraft to visit all 4 giant outer planets, using the gravity of each planet to propel the spacecraft even faster on to the next. The dream of Voyager 1 and Voyager 2 was born. July 1st, 1972, the project begins. The mission was first called the Mariner Jupiter-Saturn 1977 project. December 13, 1972, it holds its first meeting at the Jet Propulsion Laboratory. March 1977, the Mariner Jupiter-Saturn 1977 project is renamed Voyager. Unlike Voyager 1, that was only going to visit Jupiter and Saturn, Voyager 2 was to visit all 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, by using gravity assists to slingshot from one planet to the next. On August 20th, 1977, Voyager 2 launches. It's named Voyager 2 because it will reach Jupiter and Saturn well after Voyager 1. This is so Voyager 2 can take a longer trajectory to rendezvous with all 4 gas giants. September 5th, 1977, Voyager 1 launches. December 10th, 1977, both Voyager 1 and Voyager 2 enter the asteroid belt. December 19th, 1977, while in the asteroid belt, Voyager 1 overtakes Voyager 2. September 1st, 1978, Voyager 2 exits the asteroid belt, heading for Jupiter. April 24th, 1979, Voyager 2 begins its Jupiter observation phase, almost 4 months after Voyager 1. It begins transmitting images of Jupiter, allowing for the creation of time-lapse movies of its atmospheric circulation. July 9th, 1979, Voyager 2 makes its closest approach to Jupiter, flying within 580,000 kilometers or 360,000 miles above Jupiter's cloud tops. Voyager 2 confirmed many of Voyager 1's findings, providing more detailed images of Jupiter's clouds, its ring system, and moons. Voyager 2 identified the moon Adrastea, provided further insights into the dynamics of Io's volcanism, and provided details of Europa's intriguing surface, hinting at a subsurface ocean. Voyager 2 observed Jupiter's Great Red Spot, providing new details and discoveries. July 1979, Voyager 2 does a flyby of Jupiter's Galilean moons, Europa and Ganymede on July 9th, and Callisto on July 10th. Voyager 2 made additional discoveries about Jupiter's moon system, building upon what Voyager 1 discovered 4 months earlier. Voyager 2 discovered that Jupiter's Jovian ring system is only about 30 kilometers thick and extends to about 129,000 kilometers from Jupiter's center. Voyager 2 helped develop the theory that Jupiter's rings are maintained by material ejected from nearby small moons through micrometeorite impacts. These impacts kick up dust that becomes part of the overall Jovian ring system. August 5th, 1979, Voyager 2's Jupiter observation phase ends about a month after its closest approach. Between August 5th, 1979 and June 5th, 1981, as it traveled between Jupiter and Saturn, Voyager 2 remained actively engaged in scientific operations and system monitoring. This 22-month interplanetary period was a crucial phase of the mission, filled with scientific observations, engineering operations, and course planning. This period also helped scientists build models of the Heliosphere, the immense expanse of solar wind surrounding our solar system. June 5th, 1981, Voyager 2 begins its long-range observations of the Saturnian system. August 25, 1981. Voyager 2 makes its closest approach to Saturn, coming within 41,000 kilometers, or about 25,000 miles, above its cloud tops. 50,000 miles closer than Voyager 1's trajectory just 1 year earlier. Voyager 2 provided detailed imaging of Saturn's rings, revealing intricate structures, spokes, and braided features, and confirming the ring's icy composition. It also discovered additional small moons within and around Saturn's rings. While Voyager 1 was the first to observe and image Atlas, Prometheus, and Pandora, it was Voyager 2's slower, more deliberate flyby that provided the detailed imaging needed to confirm their existence, ultimately earning Voyager 2 the official credit for their discovery. August 25, 1981, Voyager 2 experienced a malfunction. The scan platform, the mechanism responsible for aiming its cameras and instruments, jammed. Engineers were able to fix it, allowing Voyager 2 to continue its Saturn flybys without significant loss of data. On August 25, 1981, Voyager 2 conducted flybys of Saturn's moons, Iapetus on August 25th, and Tethys, Dione, Rhea, Enceladus, and Mimas on August 26th. September 25th, 1981, Voyager 2 ends its Saturnian observation phase, a month after its closest approach. September 25th, 1981 to November 4th, 1985, Voyager 2 entered a 49-month-long cruise phase filled with science, system maintenance, and preparation for the Uranus flyby. Activities included probing the interplanetary medium, monitoring spacecraft health, performing instrument calibrations, and sending all valuable science data back to Earth. Engineers uploaded software enhancements, new routines to enable onboard image compression, and to implement more efficient encoded data transmission. All were critical improvements for managing the low bandwidth and power limitations during its long cruise. Ground-based systems on Earth were upgraded, major deep space network antennas were enlarged, and antenna array techniques were refined, enhancing the ability to receive Voyager 2's increasingly faint signals as it journeyed toward Uranus. November 4th, 1985. Voyager 2 began its Uranus observation phase, initiating a detailed long-range survey of the planet and its surroundings. January 24th, 1986. Voyager 2 makes its closest approach to Uranus, flying within 81,000 kilometers or 50,000 miles above its cloud tops. Voyager 2 confirmed the existence of 10 new moons: Puck, Cordelia, Ophelia, Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, and Belinda, bringing the total known moons at the time to 15. Voyager 2 also discovered 2 new rings, bringing the total known Uranian rings to 11. Uranus is unique because it rotates almost completely on its side, with a 98-degree tilt, so its poles face the sun instead of its equator. To make things even stranger, its magnetic field is tilted 59 degrees from this rotation and doesn't even line up with the center of the planet, causing a wildly uneven magnetic field that wobbles as the planet spins. Voyager 2 gave detailed images of Uranus's 5 largest moons, revealing varied surfaces and even evidence of past geological activity on Miranda, with complex chevron features and canyons. Miranda has deeply scarred cliffs, ridges, valleys, and patchwork terrain that seemed almost stitched together. It's home to Verona Rupes, the highest known cliffs in our entire solar system, stretching 20 kilometers or 12 miles high, over twice as tall as Mount Everest. Voyager 2 found Uranus to be deceptively quiet on the surface. A pale, bluish atmosphere appeared calm and featureless, but beneath its sleepy exterior lurked a surprise. A powerful internal heat source, radiating more energy than it receives from the distant sun, defying expectations for such a cold and faraway world. February 25, 1986, Voyager 2 officially ended its Uranus exploration phase. Between February 25, 1986 and June 5, 1989, between the planets Uranus and Neptune, Voyager 2 continued to collect valuable data about the outer heliosphere, solar wind behavior, magnetic fields, and cosmic rays. All its instruments remained active, collecting information from a region of space never before studied in such detail. June 5, 1989, Voyager 2 officially began its Neptune exploration phase. August 25, 1989, Voyager 2 makes its closest approach to Neptune, coming within 5,000 kilometers, or about 3,000 miles, from the planet. This was the first and only close-up encounter with Neptune to date. Voyager 2 discovered 6 new moons: Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus. It also discovered 2 new complete rings circling the planet. Voyager 2 revealed Neptune's dynamic atmosphere, including the Earth-sized Great Dark Spot, a storm system similar to Jupiter's Great Red Spot, which later dissipated, and the fastest winds in the solar system, exceeding 2,100 kilometers per hour, or about 1,300 miles. It was evidence that Neptune's weather and atmospheric activity was far more active than expected for such a cold, remote world. Voyager 2 did a close flyby of Neptune's largest moon, Triton, revealing a surprisingly active and geologically young surface, with active nitrogen geysers indicating cryovolcanism. This was a significant finding, as Triton was thought to be too cold for such activity at the time. The Neptune encounter completed Voyager 2's grand tour of the outer planets, making it the only spacecraft to have visited all 4 gas giants. October 2, 1989, Voyager 2 officially ended its Neptune exploration. October 3, 1989, Voyager 2 begins its interstellar mission with a downward trajectory south of the ecliptic plane. This is the disk-like plane in which most planets orbit the Sun. Voyager 2's wide-angle and narrow-angle cameras were turned off on 2 separate dates in 1989. The wide-angle camera on October 10, 1989, and the narrow-angle camera on December 5, 1989. This was done to free up power, computer memory, and data speed for other instruments collecting data on the solar wind and interstellar space. August 30, 2007, Voyager 2 crosses the termination shock at 84 AU, entering the Heliosheath. Voyager 1 crossed the termination shock on December 16, 2004, over 2 years earlier. This is the boundary where the solar wind slows abruptly as it encounters pressure from interstellar space. This occurred 5 years after Voyager 1 had done the same, in 2002, but at a different distance. Voyager 2's crossing provided critical comparative data between the northern and southern hemispheres of the Heliosphere, indicating that the Heliosphere is not perfectly symmetrical. Between 2007 and 2018, Voyager 2 traversed the Heliosheath, the outermost layer of the Sun's influence. During this phase, its instruments measured key changes in plasma density and temperature, magnetic fields, cosmic rays, and solar wind behavior. This data helped scientists understand how the solar wind behaves near the edge of the Sun's reach. Voyager 2 was still functioning well, though NASA had begun power-saving measures by turning off non-essential systems to keep key science instruments running. Between October 2010 to 2014, Voyager 2 detected multiple shock waves in the solar wind caused by solar storms. These shocks travel outward from the Sun and, when they reach the Heliosheath, cause dramatic changes in particle densities and magnetic field structures. November 5, 2018, Voyager 2 crosses the heliopause at 119 astronomical units and enters interstellar space, the boundary where the Sun's solar wind is stopped entirely by the interstellar medium. This marks Voyager 2's official entry into interstellar space, making it the second human-made object to do so, after Voyager 1. But unlike Voyager 1, Voyager 2 still had a functioning plasma instrument, allowing it to directly sample the plasma density in the interstellar medium, something Voyager 1 couldn't do directly. This provided groundbreaking confirmation that it had indeed exited the heliosphere. Voyager 2 detected a sudden drop in solar wind particles, a sharp increase in galactic cosmic rays, and a definite change in magnetic field direction. These changes occurred almost instantaneously on November 5, 2018, confirming the crossing. January 25, 2020, a major malfunction. Voyager 2 experienced a power overload during a routine spacecraft calibration spin. Two high-power systems accidentally ran at once. To protect itself, the spacecraft automatically shut down its science instruments. NASA engineers diagnosed the issue and were able to restore full operations by early February 2020. July 21, 2023, another malfunction. Voyager 2 temporarily lost contact with Earth due to a command error that caused its antenna to point slightly away from Earth. August 2, 2023. NASA was able to detect a faint signal indicating the spacecraft was still functioning. August 3, 2023. Full contact was restored by sending a shout command that was picked up by the spacecraft, reorienting its antenna. September 26, 2024. To save power, NASA turned off the plasma science instrument. On March 24, 2025, NASA also turned off Voyager 2's low-energy charged particle instrument. The cosmic ray subsystem is scheduled to be deactivated in 2026. In July of 2025, Voyager 2 was about 21 billion kilometers from Earth, or about 13 billion miles. This is equivalent to 139.5 astronomical units. Voyager 2 is traveling away from the Sun at a speed of about 55,000 kilometers per hour, or 34,400 miles. Like Voyager 1, Voyager 2 is powered by a radioisotope thermoelectric generator, or RTG, a type of nuclear battery which continues to provide dwindling power and is expected to power the spacecraft until the early 2030s. Voyager 2 and Voyager 1 each carry a golden record, an interstellar time capsule containing sounds, images, music, and greetings in 55 languages, meant to portray the diversity of life and culture on Earth. Encased in a gold-plated aluminum jacket, the record was designed to be discovered by intelligent extraterrestrial life, offering a glimpse of humanity's existence. A message from the human race to the endless wonders of our universe.